Hi class, today we're talking about trigonometric identities. So identities is something that we learned in grade 11 where we took a few of our known identities and proved a lot of other identities. But now that we're in grade 12, we can add a lot of new identities to our arsenal. So now we can prove a lot more things. Isn't that exciting? So just remember from last year that we learned the reciprocal identities, okay, cosecant, secant, and cotangent can be replaced with those things, okay. Tan x is, again, always useful. If you replace, anytime you see tan, you want to replace it with sine over cos. So it would make sense that anytime you see cotangent, it would be cos over sine, since it's the reciprocal identity. Okay, the Pythagorean identity, sine squared plus cos squared equals 1, and then also different iterations of that. So if you want cos squared, you could write it as 1 minus sine squared, or sine squared could be written as 1 minus cos squared. Okay, now we add two other Pythagorean identities. 1 plus tan squared is sec squared, and 1 plus cotangent squared is cosecant squared, okay? And now we add all of our double angle formulas, okay? So we learned those, and our compound angle formulas. All right, so this is directly from your textbook, I believe from page 416, 416. It's right in the key ideas area of the 7.4, the trig identity section. So this is what you will be getting on your test and on your exam, this exact sheet. Okay, so if you go to your note, it looks like this. So an identity states the equivalence of two trigonometric expressions. So then the solution is the domain of either function. In other words, the identity is true for all possible values. So unlike an equation, which can only be solved for one value, an identity is true no matter what value you put in. So you can fill in these formulas using your textbook, okay? I'm not going to spend the time filling them in for you. They're all right there in your textbook. Or you can take a moment to pause this screen and copy them down if you don't have your textbook available. All right, so let's get to work. So to prove a trig identity to be true, you have to show that left side equals right side. So we're always breaking them up. We don't want to keep it equal all the way down. We have to separate our left side and our right side. So the first thing I like to do is kind of just get a look at what I have and think, how can I make what I have look like what I have on the other side? So in this, it's clear that we have a complicated left side and a more simple right side. Okay, so I'm going to turn tan into sine over cos. Oops, sine x over cos x. Because I already have sines and coses over here, so this just gives me a better target to shoot for, just to remind myself I'm just looking for sine over cos, rather than leaving it written as tan, because I might get confused and forget that that is just sine over cos. So that's a pretty simple right side, so now I'm just going to massage and work with the left side until it looks like the right side. So sine 2x is an identity, okay? So if we go back again to here, sine 2x is just 2 sine x cos x. So I can replace it with 2 sine x cos x. So I'm just going to take out the x's just to make it easier and make it just 2 sine cos, just because they're not really necessary in terms of the proving. And cos 2x. So the thing with cos 2x is it can be represented in 3 different ways. So you got to decide the way that makes the most sense within the context. So I can represent cos 2x this way, or this way. Now notice though here on the right side, I only have cos in the denominator. So I probably want to represent it the way that only includes cos, which in this case is 2 cos squared x minus 1, because both of the other representations involve sine. Okay, so that's what I'm going to try at least. It's my first, it might not be the right choice, but that's going to be the first thing I'm going to try 2 cos squared minus 1. Okay, again, because I'm trying to get only sines on the top and only coses on the bottom. So normally I'd keep going down, but I'm just going to go to the right here because of the space on the screen. So what happens? Well, I'm just going to leave the numerator the way it is. 2 sine cos. Okay, 1 minus 1, 0. So you're just left with 2 cos squared. Well, watch the magic that I'm about to make happen. This 2, they're gone, and this cos can go off with this squared. So look at that. It is magic. I'm left with sine over cos, and my left side equals right side. And the people rejoiced. Yay. All right, fun times. We do this all day. All right, number 2. So here we have something that uses a compound angle formula again. So our left side is cos pi over 2 plus x, and our right side is negative sine x. So actually, we did something very similar to this exact problem in the compound angle note, compound angle formulas note. So we're just looking at cos as the sum of 2 angles. So that we're going to use cos A plus B. So we have cos A cos B minus sine A sine B. So cos pi over 2 cos x plus, I think, yeah, oh no, minus sine pi over 2 sine x. And look at this, cos of pi over 2 is just 0. So this whole thing goes to 0. And sine of pi over 2 is 1. So we get negative sine x. Life is good. Alrighty. Now we get into fractions. Fractions. Okay, in fractions, common denominators are king. So left side, right side. Oh, look at all these tans. We are going to have fractions galore. In fact, really, we're just going to be working mostly on this right side. So I'm going to erase and move my right side over because we're not really doing much with the left side at all. It's going to be a lot of stuff with the right side. So I could leave it as this, but I'm going to rewrite them with the compound angle formulas just so I have a better shot of knowing what I'm aiming for on the right side. So cos of x minus y, again, if you look at your compound angle formulas, can just be rewritten as cos x, cos y, technology, plus sine x sine y. Okay, all over cos x cos y minus sine x sine y. Okay, we can verify that here are cos x cos y minus sine x, and there it is. Okay, so I put it in this form just so I can have a better shot of making my right side look that way. So tan, you notice we have sines and cos on the left, so we got to change all of our tans into sines over coses. So we get fractions over fractions. It's quite a fun time. So I'm going to start writing up here just so I have a better shot of having enough room to write this. I'm going to start my right side up here. Okay, so 1 plus, so tan x is sine x over cos x. And tan y is sine y over cos y. Okay, so in this case, it is important to write the x and the y because they're different, okay? In the previous example, everything was in terms of x, so that's why I took it out. But here we have x's and y's, so you got to be more diligent with that. So sine x, cos x. So I'm just replacing my tans with sines over coses. Okay, let's take a look. That's all I did. Okay, so now I have 1 plus a fraction, okay, and 1 minus a fraction. So we need to get a common denominator. So this has a denominator when you multiply it through of cos x, cos y. So 1 will be cos x, cos y, divided by cos x cos y, right? And then we'll have plus sine x sine y all over cos x cos y. Okay, divided by, now I would have division, a fraction over a fraction, but instead of doing that, I'm going to turn it into multiplication right away. Okay, so this denominator, this common denominator, becomes my numerator. Okay, and whatever the numerator would have been becomes my denominator. So to get the common denominator here, I would have had cos x cos y minus sine x sine y. Okay, so if that stuff is confusing you, you can keep it as a fraction over a fraction and then just flip later. Okay, so all I did was get a common denominator with this big guy on the top and a common denominator with this big guy on the bottom, and then I flipped and multiplied. If you have to do that in 2 different steps, that's totally fine. Okay, but now you can see that this and this cross off, so I'm just left with what I'm supposed to be left with, right? Cos x cos y plus sine x sine y all over cos x cos y minus sine x sine y. And my left side equals my right side. Life is just fabulous. Feels good. All right. Okay. Oh boy. This doesn't look so fun, does it? So, this is one of those cases where you could turn this into a lot of work, or you could not. Okay, so your first instinct, which is what I did up here, would be to turn the sine 2x into 2 sine x cos x. So you can do that if you want. It doesn't hurt anything, but I'm going to show you a way where you don't have to, because you're actually able to massage this left side so that we just get sine 2x without having to actually do anything else. All right, so everything is written with x's, so I don't necessarily have to write the x, but because it's 2x, I'm going to. So again, you always want to look for places where you can factor. Notice that this left side has 2 terms, okay? This is one term, and this is another term, okay? And both of the terms contain tan 2x as part of it. So what does that mean you're able to do? That means you're able to take it out as a common factor. Okay, so if you take it out as a common factor, you're left with 1 minus 2 sine squared x. Now, why is that important? Where have we seen this before? You're thinking, that looks familiar, 1 minus 2 tan sine squared x. And here it is. Look, 1 minus 2 sine squared x can be replaced with cos 2x. So I'm going to do that. Now, why is this? How can we turn this into sine 2x, you're thinking? Well, I need to divide this by a cos 2x. What is going on? Oh, tan 2x can be rewritten as sine 2x over cos, oh, I'm writing in front of my screen here, hide, cos 2x. And then when I multiply that by cos 2x, oh, look what happens. These guys cross off, and I'm just left with sine 2x. Oh, left side equals right side. There we go. All right. So there's definitely more complicated ways you could have solved this. If you had turned everything into sine over cos right off the bat, that's another way of doing it. It just might take more lines. Okay. But yeah, there you go. That's one way to do it. Okay. Now we're just going to prove something is not an identity. So to prove that something is not an identity, the way you do that is to find a counterexample. So a counterexample is just one instance where something isn't true, and that's enough to prove something is not true. To prove something is true, you need to show it's true all the time. You can't use an example. But to prove something's not true, you just need to show it's not true one time, and then you can say it's not true. So, so a counterexample is any x value where your left side will not equal your right side. Okay? So I'm just going to choose going to be some values of x that will actually make this true. So don't be discouraged if your left side does equal your right side. That means you just need to pick a different one. So left side and right side. Okay, I picked pi over 2 because I know exact values, and sine of pi over 2 is pretty easy. So sine of x, so sine of pi over 2, plus sine of 2 times pi over 2. Okay, of course I wrote my right side way too close here. Okay, so, and then my right side is the sine of 3 times pi over 2. Okay, so sine of pi over 2 is 1, and sine of 2 pi over 2, that's just the sine of pi, that's 0, so I get 1 on my left side. Now the sine of 3 pi over 2 is -1. So therefore, left side does not equal right side, and so that this is not an identity. So sine x plus sine 2x does not equal sine 3x, even though it looks like that might work. It doesn't work. Proved it with the counterexample. Drop the mic. All right, so some strategies that we can use. This is a review for grade 11, but remember to separate your left side and your right side. Then you want to show that the left side equals right side, okay? Don't keep the equal sign going all the way down. You want to simplify the more complicated side first, okay? And then you want to manipulate both sides until left side equals right side. So if both sides look kind of complicated, you probably want to work on one of them till it looks pretty simple, and then try to make the other one look the same as that simple version. Okay, if one side is simple already, you might not even have to mess with it. You just want to mess with the other side until it looks like the easier side. Okay? So you want to rewrite different things using known identities. Okay? And if you're adding or subtracting fractions, you're going to need to use a common denominator. That comes up quite a lot. Okay, don't forget your factoring methods. So common factoring, you might have to common factor, as I did in that last example. You also need to know your difference of squares. Okay, so for example, if you have like cos squared theta minus sine squared theta, it might help to do it into cos theta minus sine theta, cos theta plus sine theta. Or that might not help you at all. You might want to use that and change it into cos 2 theta. Okay, it just depends what you're trying to get the other side to look like. Okay, you have to use some reasoning and to be like, is this going to help me get to where I want to go? Or is writing this as cos 2 theta going to get me where I want to go? Okay, you also have to remember, I'll put it down here, your difference of cubes. Okay, this comes up in your homework, the difference of cubes. So that's a minus b, a squared plus 2ab, that's a 2, plus b squared. Okay, that comes up for sure. Remember a cubed plus b cubed, that can be factored as a plus b, a squared minus 2ab plus b squared. All right, and always write tan as sine over cos. All right, so those are the same strategies that we learned in grade 11. They're still useful today. The only new additions are the difference of cubes and the addition of cubes, as well as our compound and double angle formulas. So thanks for watching, guys. Have fun with these trig identities, and as always, I hope you learn lots.